Greetings, Astronomy 10, and welcome back to your Chapter 15 lecture. This will be the first of two lectures on Chapter 15, and today we're going to start talking about the Milky Way, the galaxy which our star, our sun, is just one of 100 billion stars, one member of a huge family. Now, we know that we live in a galaxy called the Milky Way, we know what the structure is, we know what it looks like, we know about how many stars are in it, and so on. But how do we know all of this? How do we know what the Milky Way looks like? There are several images of the Milky Way in today's image bank. But are they accurate? How do we know? If somebody told you that they had an actual photograph of the Milky Way, would you believe them? Well, I certainly hope not, because in order for them to have an actual picture of the Milky Way, they would need a selfie stick that was like 50,000 light years long. It's impossible, right? We're in the Milky Way, and so we'd have to get way, way out of it in order to take a picture of it, and we can't do that. So, how do we know what it looks like then? How can we be sure? We have maps and stuff of it, right? We have plenty of not star charts, that's not the right word, but like galaxy maps. Actually, National Geographic has a really nice one, but we couldn't use it because, copyright reasons. But how do we know? So let's start with what the Milky Way looks like from the surface of the Earth. What does it look like? And if you've lived in a large city your whole life, you may not have seen a whole lot of it. But if you go to any place that doesn't have a whole lot of light pollution, you can see that it just looks like a big streak of kind of milky looking material in the night sky, right? Obviously you can't see it during the day because the sky is blue, and that blocks out pretty much all the celestial bodies except for the sun and the moon. Sometimes you can see Venus, there are some other occasions where sometimes you can see the planets during the day, but generally not so much, right? Objects have to be really, really bright for you to see them during the day if they're outside of our atmosphere, because it turns blue during the day. So, at night, sometimes you get to see the Milky Way, and it looks like somebody spilled a bunch of milk across the sky, right? It has that kind of liquid, flowy, but kind of white and creamy, glowing kind of look to it. And as a matter of fact, the word that we have for galaxy comes from galactos. I think that's from Greek. And that, of course, means milk. We used to think that, it looked milky. We kind of maybe still do. I mean, if you try to take a long exposure like the fifth image in today's image bank, number 5, the first 4 are kind of zoomed out renditions of what we think that the Milky Way probably looks like, and the 5th one is a picture from the surface of the Earth, right? And that one, if you take a really long exposure, you can see that it's not just, a bunch of milk. You can see that there are, some lighter parts and some darker parts because there's lots of gas and dust in the disk of the Milky Way, like our models predicted. So how do we know what it looks like? Well, if we look up at the night sky and we see the Milky Way, it kind of looks like a disk, right? So it's probably not an elliptical galaxy, and it's really kind of flat, so it's probably not an irregular galaxy either. So we've narrowed it down basically to a spiral arm galaxy or a barred spiral galaxy. But which one is it, and how do we know? Well, in order for us to say for certain, we need some way that we can see through the gas and dust that make up the disk of the Milky Way. So let us remind ourselves of how spectra work in order to try to piece this together. So if an object warms up enough that it emits light from heat, it's a black body radiator like turning on your stove, your electric stove, or something like that, right? Something that emits light from heat. It emits light of all colors, all frequencies, obviously some brighter than others, depending on the temperature of the object, right? The hotter this object is, the bluer the color, right? The more that the peak transmission moves towards the high energy, high frequency, short wavelength end of the electromagnetic spectrum, right? The cooler it is, the more the opposite is true. The longer wavelength, lower energy, lower frequency, peak electromagnetic radiation that it's going to emit. Or, for shorthand, we usually just say the redder for long wavelengths, low frequency, low energy, right? And bluer for the opposite. So the hotter something is, the bluer the peak color. The colder something is, the redder the peak color. That was Wien's displacement law. Black body radiators emit a continuous spectra, but the peak will tell us kind of what the temperature is, right? So, if you have an object like your stove, it's going to emit a continuous spectra, with some colors brighter than others. Now, obviously, the Milky Way is not a black body radiator, right? There's gas and dust in the disk, and gas and dust like that, obviously, those will absorb a bunch of the light and scatter it, right? Energy has to be conserved, and so the light that gets absorbed by the dust has to be re-irradiated, right? But it's going to re-irradiate it in all possible directions, right? Essentially scattering it, dimming it out, and making it much more difficult for any of that light to get straight through the disk. That becomes a mathematical impossibility almost, right? After so many dust particles, the likelihood that a photon is going to keep going in a straight line is very, very slim. So, what else? What else could possibly clue us in? Well, recall also that continuous spectra are not the only kind of light spectra, right? Strictly speaking, the light emitted by a star like our sun is continuous, but all stars, like our sun, have atmospheres, and these outer atmospheres will absorb and re-emit some wavelengths of light, the ones that correspond to the emission lines for the gases in that atmosphere, right? And so because the atmosphere is going to scatter the light from the star, it looks like those emission lines are missing. And so generally when you look at light from a star, you get an absorption spectrum, right? We've seen that before. There's also an image of that in today's image bank. That's the 19th one, I think, the sun spectra. In any case, you get an absorption spectrum, right? However, if you look at just the gas by itself, if you were to turn your spectrometer at just the corona of the sun, you would see just the emission lines, right? The hydrogen emission lines for the hydrogen, the helium emission lines for the helium, and so on, because those photons, right, those specific wavelengths of light are being emitted by that gas, being absorbed from the sun and emitted again by the gas, obviously in all possible random directions, right? That one, of course, we call an emission spectrum. So we've got a continuous spectrum, an absorption spectrum, and an emission spectrum, right? Those are our three main general kind of spectra types. Now we can't see what the Milky Way looks like because any light emitted by the disk of the Milky Way is obscured by the gas and dust in it, right? So any of the stars or the nebulae that make it up, the gas and dust in the disk of the Milky Way is going to make it nigh upon impossible for the light to travel straight through and, somehow get to us. So the only way that we could actually see the shape of the Milky Way would be if the gas and dust itself gave off some kind of light, some kind of electromagnetic radiation, something that wouldn't get scattered by the gas and dust. But there isn't any such thing, right? Or is there? Remember that a hydrogen atom, uh, as a hydrogen atom occurs in nature, it's just one proton and one electron in its ground state orbital. But that electron can have two possible energy states. Remember, we called that spin up and spin down. Right? It could be spinning one way or spinning the other, either against or with its orbit, or spin-orbit coupling. So you can imagine, let's say there's a hydrogen atom in a cloud of gas somewhere in the disk of the Milky Way, right? And it's got one electron, and that electron is spin up. Now remember, there's a subtle energy difference between spin up and spin down. And as a matter of fact, there's a very tiny amount of energy difference, so it is possible. It doesn't happen very often. I think a hydrogen atom is supposed to do this randomly once in 100,000 years or something. But if that one electron goes spontaneously from spin up to spin down, it will emit a very long wavelength form of electromagnetic radiation, a photon, light, whatever you want to call it. And that wavelength of light, for it to be absorbed by another hydrogen atom, it would have to be, an electron that's spin down and have it go spin back up. It's not very likely, right? And definitely the dust in the Milky Way is not going to absorb that because it's just too long, right? It's essentially radio wave. Radio waves, like this 21 centimeter electromagnetic radiation that gets emitted from an electron going from spin up to spin down, go pretty nicely through the gas and dust that make up the Milky Way. It's sort of too long to absorb. And so it kind of travels freely throughout the gas and dust that make up the disk of the Milky Way. We call this 21 centimeter radiation the forbidden band, for the reason that it is forbidden by classical mechanics. We have to invoke quantum mechanics in order to explain its existence. But it does exist. And not only does it exist, it is incredibly common all throughout our own galaxy. And once we realized this, once we, attuned our radio telescopes to look for 21 centimeter radiation, we saw that there were tons of sources for it and that it was traveling all throughout our galaxy. We found lots of Class O and Class B stars in the disk structure, and after we used this 21 centimeter radiation, we were basically able to map out our own galaxy. And then we compared it to the 21 centimeter radiation that we found in other spiral arm galaxies, like the Andromeda galaxy. And we knew then that we were in a spiral arm galaxy. In the 90s, we used infrared astronomy in order to find out that there is a large bulge, a central structure at the center of our galaxy. And so we learned a few things from that, right? We're able to map the galaxy out. But we still had several questions, one of which was exactly how big is the Milky Way? What are its boundaries? How far do these spiral arms go? And the answer to that lies in a type of structure we call a globular cluster. A globular cluster is a small but very dense cluster of stars. It generally has fewer than 1 million solar luminosities, so it has 1 million stars or fewer generally. but it's in a very small space, generally only about 15 light years across, so it's very tightly packed. And as such, these globular clusters are typically very bright. They're very high in the luminosity. Only about a quarter of these globular clusters exist inside the disk of the Milky Way. The rest of them are outside the disk. Where would that put them? If you remember, that would put them in the dark matter halo, the spherical structure that sort of envelops the disk of the Milky Way, and galaxies like ours. But how do we know for sure? Well, a population of stars that dense has to have at least a few variable stars in it, right? As remember, as high mass main sequence stars evolve off of the main sequence, they go through that portion of the HR diagram we call the instability strip, where they're kind of zigzagging back and forth, right? They they pulsate because they kind of build up a helium blanket around the core, and they bottle up a bunch of energy, making the star shrink and get dimmer. And then as that energy builds up, it makes that helium blanket expand, and the star pulses, it gets bigger and brighter. That, yeah. And so doubtlessly, if you have like a million of those stars, sooner or later you're going to see some variable stars. And so plenty of them, fortunately, have things like Cepheid variable stars or RR Lyrae stars, which the astronomer Henrietta Leavitt discovered have a period luminosity relationship like Cepheid variable stars around the turn of the 20th century. And so we were able to map out the distance to these globular clusters, most of them pretty readily. Globular clusters like Messier Object 92 or M92 are quite old, having a main sequence turn-off of about 13 billion years, meaning they're much older than the Sun and almost as old as, in fact, the entire universe. Remember, the universe is about 14 billion years old or something like that, thereabouts. So, long story short, literally no young globular clusters with a zero age main sequence distribution, or a very young, few million year main sequence turn off have been detected. They're all very old. So we made a 3D map of the galaxy with globular clusters in them and their positions, and it was obvious what it was they were orbiting. Obviously, that means, if they're all kind of moving about in three-dimensional orbits, they have to be orbiting the center of our galaxy, right? The hypermassive black hole at the center, which we'll come back to. And that put the center of our galaxy, the core, the central bulge, whatever you want to call it, about 27,000 light years from where we are now. Now, our own sun, the star that we're orbiting, is not nearly this old, right? It's about 5 billion years old, and that's about 8 billion years younger than the 13 billion year old globular cluster stars. So obviously our solar system formed in the same molecular cloud or nebula or whatever you want to call it that the sun came from. And stars like our sun that are near us, that are moving through the disk of the Milky Way, are unlike the stars in the globular clusters, right? Stars that came from the same cloud of gas are often called an open cluster. And they're typically just, a few stars, up to maybe, a few thousand maximum, but anywhere from maybe a few dozen or less is a typical number for an open cluster. Stars in an open cluster generally have masses depending on how much gas fell into the star. Obviously, if it was a very dense gaseous region, you might have, some O or B class stars. But if it was more diffuse, you're going to have, class M stars maybe. So it really just kind of depends. Nonetheless, if you manage to locate a fresh open cluster, then you should see a zero-age main sequence distribution, right? Basically the entire range of main sequence stars from class O to class M. So that means there should be bright hot stars, big ones, as well as small, cool, low mass stars, class O, class M. Now these clusters don't necessarily stay together forever. The tidal forces due to, other clusters or other stars or hypermassive black holes or whatever can cause stars to move at different velocities relative to each other. And so sometimes they can kind of get separated. Which is nice in theory, but why should we care? Well, what this means is that stars in the disk are generally younger. The population of stars in the disk are generally younger because, star formation is going on here. But stars out in the halo are old, right? Globular clusters. And so that means the stars in the halo formed a long time ago. They formed first. When the universe was much, much younger, just after the Big Bang, some 13.7 billion years ago, there was only hydrogen and helium and maybe a little bit of boron, element 3. And as stars were born and died, they made heavier elements in supernova events. If you remember when we talked about the evolution of high-mass main sequence stars. Old stars, like the ones from the first generation of stars, like these 13 billion year old stars in the globular clusters, have little to no heavy elements in them. Because they were made of the original material and didn't get made of stars that got blown up and went supernova and made heavier elements, right? Younger stars like the sun have evidence of heavier elements in their absorption spectrum. And if you look again at the image, I think it's the 19th one, right? That was the one that we figured. I really need to blow my nose. The spectrum of the sun has absorption features corresponding to about 70 or so elements. And so, obviously, the sun is not made up of just hydrogen and helium. So the cloud of material that made up the sun is also made up of material from an older generation of stars that died and went supernova and made heavier elements, right? What we call stellar processing. Thus, the absorption spectrum of a star can tell us about the prevalence of heavy elements in the portion of what we call the interstellar medium, or the stuff, the material in between stars. In that area of space and time, in the Milky Way, or whatever galaxy, if you're looking at, stars in another galaxy, around the time that that star started to form. Stars in globular clusters, as you might imagine, have very, very few of these absorption features because they're very old and so they didn't get subjected to a lot of stellar processing, right? Stars in the region of the disk and closer to the center of the galaxy have a greater abundance of heavier elements as a result. And that means star formation must be happening more towards the central bulge. All right, stands to reason. You see more heavier elements. That means that there's more stellar processing. The material kind of mixes quite a bit, though. As supernovas happen, they can cause material to be ejected from inside the plane, sort of above or below it. And then this material, because if all this material gets ejected like up above the plane of, say, the Milky Way, right? All of the materials below it, and so gravity is going to pull it back down. But it doesn't necessarily go straight up and straight down. It could go inward or outward or whatever, and so it kind of gets scattered. So it mixes some. And in any case, long story short, that's kind of how we know how the material in the Milky Way, and indeed in all galaxies, sort of become enriched with heavier elements. Now, most globular clusters have a small but non-zero amount of heavy elements, and thus even these globular clusters were not the first stars to form in our galaxy, right? The universe is something like 13.7 billion years old, and these globular clusters are something like 13 billion years old. So there was, 700 million years of stellar processing before they formed. So that means there must have been at least one previous generation of stars. Every star, however, that is below 0.8 solar masses has a longer lifespan than the current age of the universe. And that means that every star below this mass threshold that has ever been is still around. Right? Anyone that has ever been made that is below 0.8 solar masses is still around today. There are plenty of low-mass stars, especially, in our own neighborhood in the Milky Way, but none have zero heavy elements that we've been able to find. Thus, the dust and gas in the Milky Way has all seen some star formation, even if just a little, with a greater concentration in the disk and an even greater towards the central bulge. But how much material is actually there? How much of these heavy elements are there? So even in a young star like our Sun that has seen probably close to 9 billion years of star formation before it was formed, has less than 2% heavy elements. Most of it is still hydrogen and helium. And what that means is, compared to the ultimate age of the universe when things will eventually fizzle out and end, the universe is still very young. If we look at sort of a cross-section of the Milky Way, we can see that the bluer stars, the larger, more massive, hotter ones, are concentrated more in the mid-plane of the disk, which is only about 1,000 light years or so thick, which is like 1% proportionately of the entire length of the Milky Way's disk, right? And older, redder stars are found further out from the midplane, above or below, in the disk of the Milky Way. And this seems to suggest one of two things. Either there is greater star formation in the midplane, or we're capturing material from other galaxies, like the Sagittarius dwarf galaxy. Now, that second one is true, for sure. We are cannibalizing the Sagittarius dwarf galaxy right now. But it is also possible that over the course of time, stars that get generated in the midplane drift outward through gravitational interactions. Combine that with supernovae and other strong phenomena, and that gives us a pretty solid picture of what the Milky Way is actually made of. Globular clusters in the halo only make up about 1% of the galaxy's mass. There are plenty of stars that have strong red and blue shifts, meaning they're moving very fast relative to us. We call them high-velocity stars. And their orbits are similar to comets in that they sort of orbit the galactic core. Most of these stars are metal poor, meaning they're very old, right? There's not a lot of heavy elements in them. And some of them are even moving against the rotation of the galaxy disk, right? So they were probably captured from another galaxy. Not terribly unlike the large and small Magellanic Clouds, the dwarf galaxies that we are also currently absorbing in addition to the Sagittarius dwarf galaxy. There is some evidence that there's also a cloud of gas that extends about 300,000 light years in all directions from the core, from the central bulge of the Milky Way. And X-ray astronomy has shown this gas to be quite hot, something like 2 million Kelvin, but also very diffuse, very thin, not a lot of particles, right? And as such, it cannot account for the missing mass in the dark matter problem. Just like globular clusters can't either, right? They only make up about 1% of the mass. But what we do know is the galaxy also has a very strong magnetic field. Now, to put this in proper context, it's about 100,000 times as strong as the Earth's magnetic field. And the source is all of those moving gas and dust particles. And the reason that we know that is, if you remember the synchrotron radiation, that's our answer. But the synchrotron radiation from the galaxy's magnetic field is not like the synchrotron radiation that we're familiar with. It comes from a very highly energetic kind of particle that we call a cosmic ray. Now, a cosmic ray is not a ray like a beam of light like we once maybe thought it was. If you look at a really old map of electromagnetic radiation, they used to kind of think that cosmic rays were even higher energy EM radiation than gamma rays, but we know now that that's not the case. If you wanted to try to put this into context, they're essentially a very highly charged particle, and when they enter, say, the Earth's atmosphere, they collide with one particle in the Earth's atmosphere, like oxygen or nitrogen or something like that, and it essentially obliterates that particle and itself, causing a huge cascade of smaller particles to rain down in a very highly energetic fashion. And in order to put that in a proper context, one of these particles has maybe 100 joules of energy. And to try to figure out what exactly 100 joules is, if you took, say, your textbook, that's about 1 kilogram, right? 2.2 pounds. If you took that and you dropped that from a third-story building, the amount of energy that it would have when it hit the ground, if you dropped it from the roof, right, it would hit the ground pretty hard. Well, you can imagine a microscopic particle that has, what is it, 10 to the minus 19 kilograms or something like that, some itty-bitty little particle having that much kinetic energy when it hits something. That's the kind of energy that we're talking about, right? It's really, truly tremendous. So when a particle like that enters our atmosphere, it's no small wonder to think that it obliterates itself and whatever it hits and makes this huge cascade of high energy events as it falls towards the ground. Now, the glow of our galaxy can be explained by this synchrotron radiation from these extremely energetic particles. And if we compare that to the magnetic field energy if we compare the magnetic field energy to the energy of a cosmic ray, they're about equal. And that's no coincidence, right? It's because they're one and the same. Okay, that's it for today. We'll pick it up next time with part 2 of chapter 15, and we'll wrap this chapter up. If you have any questions, of course, get a hold of me through the normal channels, and we'll see you next time.